EDX Mechanics 1, Mechanics Basic Principles. Quantities in mechanics. Using the correct units will be increasingly important to you in mechanics. We use what is called the System International, or the SI unit, which standardizes the metric units we use. All standard units are based on being able to measure mass, which is a kilogram, being able to measure distance, which we use a meter, and being able to measure time when we use seconds. For convenience, we have other related units such as 1,000 grams is a kilogram, 1 kilometer is 1,000 meters, and 1 hour is 3,600 seconds. It's really important in mechanics that we can see the distinction between scalar and vector quantities. How we use units depends on the context of the problem and whether we are dealing with a scalar quantity and or vector quantities. Scalar quantities only have magnitude or size. For example, mass, distance, speed and time are scalar quantities. They only have size. They do not have direction. Vector quantities have magnitude and direction. For example, displacement, velocity, acceleration and force are the main examples we'll be using at the moment. So if we think about scalar quantities, for example, the speedometer in a car does not tell you the direction the car is travelling. It is only telling you how fast the car is going because it is measuring speed. A pedometer tells you how far you have travelled, but it does not tell you your location. It doesn't tell you where you are, so it is only measuring distance. If we now look at vector quantities, which have magnitude and direction. For example, when I throw a ball up in the air, I know that it will accelerate downwards due to the pull of gravity. So the acceleration is downwards, and I know the direction of that acceleration. It is a vector quantity. In a tug of war, the pulling forces will be in opposite directions. I know the force pulling to the right is going to be the same as the force pulling to the left if the teams are equal. I know the directions of the forces because they are vector quantities. Always check the quantities stated in a question and use the appropriate vocabulary at all times. It is possible to use either scalar or vector quantities as long as you use them correctly and in the required context. For example, if an object moves backwards 5 meters, we might say its displacement is minus 5 meters. If forward has already been defined as being our positive direction. Or we might say the object has moved a distance of 5 meters backwards. Both are fine as long as we choose our words carefully. So in this example, we have a graph which is showing the journey of Jane, who's got to travel 160 meters along a straight road to a bus stop. She's produced this graph at school to show a journey. Can you see a problem with this? At the moment there is a problem with this graph because the vertical axis is labelled distance, and distance is a scalar quantity and distance cannot decrease. So there is a problem between 50 and 70 seconds where the distance is decreasing. A much better label is distance from home. So we've got a reference point of the house. So distance from home is a much better quantity to measure. So now if we describe the journey just using scalar quantities, I could say, for example, she travelled a distance of 100 meters in the first 50 seconds. She then travelled backwards a distance of 60 meters in the next 20 seconds. She then travelled forward a distance of 120 meters, and at 100 seconds she was waiting at the bus stop. If I use the vector quantity of displacement, I could describe this as she travelled forwards with a displacement of 100 metres in the first 50 seconds. Between 50 and 70 seconds, her displacement was minus 60. Between 70 and 100 seconds, her displacement was a positive 120 metres until she arrived at the bus stop. So, if we look at the first 50 seconds, the distance travelled in the first 50 seconds is 100 metres. Her displacement in the first 50 seconds I could describe as 100 metres. Let's assume that travelling forwards is positive. Her speed in the first 50 seconds would be the distance over time. So that would be 2 metres per second. Her velocity in the first 50 seconds would be the displacement, which is 100 metres of displacement over time. So 2 metres per second. So when she was travelling forwards, her speed and her velocity gave the same value. However, if we now look at the first 100 seconds, her distance now will be different. Her distance in the first 100 seconds is 280 metres because her distance increased by 100. Then when she was going backwards, her distance increased by an extra 60. And then when she was walking forwards, her distance increased by 120 metres. However, her displacement in the first 100 seconds is different. That is 160 metres of displacement because her displacement went up by 100 metres. Then when she was going backwards, her displacement from the start went down by 60 metres. Then when she travelled forward to the bus stop, her displacement went up by 120 metres. So her average speed in the first 100 seconds, she travelled 280 metres in 100 seconds. That's 2.8 metres per second. But her average velocity is her displacement, which was 160 divided by 100 seconds. So that's 1.6 metres per second. So in everyday language, we often talk about speeds and distances, but in mechanics, it's often more advantageous to talk about displacements and velocities. So we can see the methods there. So here we have a graph showing the distance along a road of a car and a motorcycle. So I'll just give you a second. You can pause the video if you like to describe what has happened to the car and the motorcycle. So here it's distance along the road. So if we look at the car first, I can see this is a straight line. So that's telling me on this distance along the road against time graph that the car was travelling at a steady speed. However, if we look at the motorcycle, I can see that the gradient's increasing. The gradient's getting more and more. So I know that it is going faster and faster. So this motorcycle is gaining speed or gaining velocity as because the gradient's increasing. Two other interesting features. I know that the motorcycle overtakes the car at 4 seconds because that's when they have the same distance along the road. But there's also a point when they have the same speed, and it's about 1.5 seconds. The gradient of this distance time graph for the motorcycle is pretty much the same as the gradient of the car. So at about 1.5 seconds they have the same speed. If we break it down into a little bit more detail, I can see that every second the car has gained 10 metres, and that happened every single second. So I can say that the speed of the car is 10 metres per second. Notice the notation. It can be written as metres per second in that form, or using laws of indices we can write it as metres per second, like that, metre second to the -1. However, if we look at the motorcycle now, So in the first second it gained 5 meters. In the next second it gained 10 meters. In the next second it gained 15 meters, etc. So if we look at every second, on average the motorcycle is gaining a speed increase of 5 meters per second. So on average its speed increased by 5 meters per second. So if it's gaining 5 meters per second every second, we can talk about its acceleration. Its acceleration is 5 meters per second, and again, nice neat notation, we could call that 5 meters per second squared. In the next session we'll be looking at modelling in mechanics.